Hello, welcome back. The title of this lesson is called Simple Organic Compounds. This is part one. I'm incredibly excited to teach you this because in this lesson, we're going to crack the door open and take a small little glimpse into the incredible world of organic chemistry. So up until this point, we've learned about inorganic chemistry, metals and nonmetals and polyatomic ions and so on. But it turns out that there is an incredible richness of molecules that are formed just by connecting long carbon chains together with, of course, other elements as well. And that's the realm of organic chemistry. Now, the definition of what an organic compound is it needs to contain carbon and it needs to contain hydrogen. And that is going to constitute an organic compound. Now, it can contain other additional elements as well, often oxygen, nitrogen, even other compounds, other elements as well, but it must contain carbon and it must contain hydrogen. So, for instance, if you consider some of the compounds that we have learned about before, for instance, carbon dioxide is just carbon and oxygen. That's not considered organic, even though it does have carbon in it, there's no hydrogen. Same thing with carbon dioxide, carbon monoxide. So we have to have carbon, we have to have hydrogen. Now, I don't want to blab on and on in the beginning here. I want to start to show you graphically the richness of these. So what we want to talk about in the beginning is what we call a hydrocarbon compound. A hydrocarbon is just what the name implies. It contains hydrogens and carbons, but that's it in the compound. It turns out because carbon can bond in so many, in a variety of ways, you can make very long chains of carbon backbone structures, and they can have very interesting shapes in 3 dimensions. And that gives rise to all of the variety we have in biological chemistry, biochemistry, because, for instance, DNA is a very long molecule that has lots of carbon chains in there, right? Now let's turn our attention, before we go look at the pictures of what these molecules can look like, let's take a look at carbon in specific, and let's look at hydrogen. Now we know from the periodic table that carbon is going to want to accept 1, 2, 3, 4 more electrons in order to have a valence, an outer electron shell that looks like neon, right? So because of that, carbon can form 4 bonds, right? It wants to have 1, 2, 3, 4 more electrons. Now hydrogen only has 1 electron, and it would love to grab an additional electron to look like helium, which is its nearest noble gas. Noble gas on the periodic table. So carbon is trying to look like neon to gain 4, and hydrogen's trying to look like helium to gain 1. So basically they're a match made in heaven, right? Because carbon is going to want to be able to have 4 bonds. Each of the 4 bonds, if it were a hydrogen, then both partners would be happy, right? Because the hydrogen wants an extra electron, and the carbon wants to make 4 bonds, each one having an extra electron as well, and so they can both be happy, right? Now I want to show you graphically on the computer what that's about, but before we jump into that, I'm going to show you this so that you can at least have some of the names in the back of your mind. Now we're going to talk about these in great detail and draw pictures, so don't stress out about it, but we have these prefixes. Notice we have methane, which we already know is CH4. That's a combustible gas. Okay, and notice that we have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. They all end in ANE. The ANE is a hydrocarbon suffix that means that there's only single bonds between the carbons, okay? If you have double or triple bonds, that's stuff that we learn later on for even more variety of structures you can have with carbon. Carbon structures are kind of like Legos. You can build different shapes with them, and they can form very interesting shapes, okay? So the prefixes, methyl or methane means 1 in this context, 1 carbon. Now, because there's 1 carbon and it wants to make 4 bonds, then it's going to bond to 4 hydrogens. So we have CH4 for methane. Ethane is when you have 2 carbons, and we're going to learn later why, but you need 6 hydrogens to fill up all the extra bonds that surround the carbons in that case. So methane, ethane, propane. Prop means 3, so there's 3 carbons. Butane means 4 carbons. Pentane, and then here it goes by the normal prefixes. Penta means 5, hexa means 6, hepta, octa, nona, and deca. So the first 4 are a little bit different from before, but after we get to pentane, it's the same prefixes that we've used to name any molecules. Now, I don't want to talk any more about names. I want to go to the computer and show you what these molecules look like so that we can front load the richness of what we're talking about. And after we do that, we'll come back here and we'll draw the pictures and show more definitively how we write all of these down and how we solve problems. All right, now welcome back. Here we have the molecule known as methane. The dark gray in the center is the carbon, and connected to it are 4 different hydrogens. Carbon wants to form 4 different bonds because it wants to accept 4 additional electrons from the periodic table, and hydrogen is a nice atom that has an extra electron, so everybody can be satisfied. Each of the hydrogens kind of donates its electron in the sharing, so the carbon gets the 4 electrons, and the hydrogen, since it's sharing with the carbon, also feels like it has 2 electrons as well. So the carbon and the hydrogen both have enough electrons to be happy and to look like their noble gas that's close to them. So here we have methane. It's a simple molecule. Notice the angles here. The angles, when you actually calculate what this angle should be here between all the bonds, it works out to be 109.5 degrees. We're going to learn about that later and why that is, but it's important. So just kind of notice what these look like in 3-dimensional space, and then we'll go on to the next one. So this is the simplest hydrocarbon. 1 carbon, 4 hydrogens. Now let's go and increase the number of carbons and see what that looks like. So down below, we have the next one in our list, which was, remember, methane was the first one. This one is ethane. So there's 2 carbons here, and notice that the carbons are connected to each 3 hydrogens, 1 on each end like this. And so you can see that if each carbon, which is the dark gray, is connected to 4 things. It always wants to form, or almost always wants to form, 4 different bonds. So this left-hand carbon over here is connected to 3 hydrogens, and the other carbon, that's its 4 bonds, and then a similar thing is going on over here. So again, notice that the hydrogens are not exactly lined up when you look at them end on. We're going to talk about why that is in a minute, but you can see that it's very easy to understand. 2 carbons connected by a single bond. Each of the carbons is, again, connected to 3 hydrogens. All right, now let's go on to the next one. After 2 carbons is 3 carbons, and 3 carbons, we call that propane. So you might use propane in a barbecue pit or something to cook some hamburgers, and or whatever in the backyard. So this is what propane looks like. It's a bent molecule, notice, because these angles that want to be formed in the bonds, they generally want to form 109.5 degree angles. We're going to talk about a lot why that happens later. So it's a little too much to get into right now, but the angles are basically the same as they were in the previous. Notice you have this carbon connected to the 3 hydrogens, and it's connected to another carbon, but the angle comes back down so that it's still that 109.5 degree angle in all cases, and that's why it looks kinked like that. It doesn't want to form a straight line, literally a straight line molecule, and the reason is because everything wants to spread out in 3-dimensional space, and everything wants to... Basically, these hydrogens are repelling, the electron clouds around all of these hydrogens are kind of repelling each other. So the molecule can twist and turn and bend in such a way to get everything as far apart as it can. And this in propane with 3 carbons is what it looks like there. All right, now after we add another carbon, we get to a molecule called butane. And here it is right here. So here we have 1, 2, 3, 4 carbons. But again, each of the carbons has 4 bonds. Notice the outermost carbons over here in the ends, they're connected to 3 hydrogens on this end and also on this end. But the innermost carbons, they're only connected to 2 hydrogens because the carbons are connected to each other. And so, for instance, this carbon is connected to 1, 2, and then 3, 4 different 4 bonds here, basically. And then this carbon is also connected to has 4 bonds. So everything has 4 bonds, and that is in general how carbon likes to behave. Now notice that it's kind of kinked up into almost like a half circle, but you have to remember that these things can twist and turn and sort of unfold, and they're kind of vibrating and doing all of that in real time. So that's butane. Now, when we add another carbon, we get to pentane. This is a 5-carbon chain. 1, 2, 3, 4, 5. But again, notice that the carbons on the end have 3 hydrogens, this one and this one, but every interior carbon only has 2 hydrogens. But again, every carbon has 4 bonds. And it's kinked in such a way because in general, carbon, when it bonds, it likes to have that 109.5 degree angle if possible. which is what it's basically trying to do here. But keep in mind that when this thing is under, is at some temperature and it's vibrating, I mean, the bonds can twist and turn to try to keep everything spread out as far as it can spread out in three-dimensional space. All right, now, after we get to that, I wanted to show you of an interesting situation. So this was called pentane right here in a straight form molecule. But once the chain gets long enough, it can bend back on itself and create rings like this. So this is also pentane, but it's in a different shape. It's called cyclopentane. And it basically bends back on itself and it bonds back the two carbons at the ends, which is what we were looking at, right here. They bend back on themselves and connect and bond basically back to their starting point. Now you still have hydrogens everywhere, so each of the carbons is now connected to two hydrogens everywhere and to two carbons, and it forms a nice chain. But notice that this chain here, this circle, this ring, is not exactly flat in the plane. If you kind of look at it, it's kind of kinked, right? And the reason it's kinked is because it's trying to maintain this 109-degree angle, but it's difficult to do without having enough carbon atoms. And so what ends up happening is it just kinks itself and tries to get as large of an angle as it can between the carbon atoms. So they don't usually lie in a flat plane. They're trying to all spread out and get as far away from each other, and so the molecule is basically relaxed and not under any in any kind of like internal pressure from the bonds, basically. So that's a 5-carbon chain. Now let's take a look at a 6-carbon chain. This is hexane. So this is a straight molecule hexane. Again, it can rotate. These bonds can rotate around. So you see 1, 2, 3, 4, 5, 6, and you see the pattern now. The end carbons, again, each have 3 hydrogens. The interior carbons have 2 hydrogens. And what do you think is going to happen if this thing connects back on itself to form a ring? It's going to form cyclohexane. So as in hexane being a 6-carbon chain, you can form cyclohexane where it connects back on itself. And again, notice how it's kinked. It's kinked because these carbons want to have as big of an angle, as maximal angle as possible between them. And it can get a bit bigger angle if it's kinked like this, right? Because everything wants to be spread out. Now we learn in organic chemistry why the angles are the way they are, exactly what the angles and the shapes are here, but you can see it three-dimensionally, that's what it's doing. And every carbon, again, is connected to 2 hydrogen atoms. Right, so that was cyclohexane. Now here is a 7-carbon chain called heptane, and you can see we have 1, 2, 3, 4, 5, 6, 7, and this is just a straight chain heptane. And then after that we get to octane. That's an 8-carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. This is a straight chain octane. Now what happens if you try to connect this thing in a circle? Well, it looks like I didn't do that. I did it for decane, so sorry about that. So that's 8-carbon chain. This is a 9-carbon chain called nonane. And the reason it's all kinked and weird like this is, again, just because in three-dimensional space the molecule is trying to spread out and relieve the tension. It doesn't want to be balled in on itself because all of these hydrogen atoms, the white ones, the electron clouds that are around them are all repelling each other. And so basically the bonds between the carbons are swiveling in such a way to get everything as far apart as it can. So that's nonane, a 9-carbon chain. And then here is decane, which unfortunately is small. I don't know if I can get it any bigger. I guess I can make it a little bit bigger. Here's decane, and if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same thing, the carbons on the end have 3 hydrogens, and all the interior ones have only 2 hydrogens, but it's more or less straight, and it unfurls itself as much as it can to have maximal distance between everything. But this can form a ring as well, and this is what cyclodecane looks like. It's not pretty because it's not what you would expect, like a flat thing, but notice that it's kind of trying to unfurl itself in three-dimensional space. It doesn't want to be flat because it wants to have as much maximal space between everything as possible because, again, all of the electrons in these hydrogens and also in these carbons are all repelling each other. So it's bonded, but it's also trying to spread out at the same time, and that's why the shapes look a little weird the way they do. All right? After that, I want to go and show you something interesting. Let's back down a little bit to, that was a minute ago cyclodecane. Let's go back to cyclohexane. 1, 2, 3, 4, 5, 6 carbon atoms. This is what cyclohexane looks like. Now, it's a fairly stable molecule because the carbons can spread out in such a way that there's no strain inside these bonds. See, the bonds in the carbon, they like to be at 109.5 degrees, and they're able to do that better whenever you have more carbons connected to each other because they can spread out. So this is a 6 carbon chain arranged as a ring. What happens if we go down 1 carbon to cyclopentane? You can still connect them, but there's going to be a little more strain on the molecules because it's a little harder for everything to spread out. So that's a 5 carbon chain. But what if you get to something like cyclobutane? This is a 4 carbon chain. And now suddenly, in order to connect it, basically these angles are very close to 90 degrees right here. And that's far away from 109.5 degrees, which is what the carbon wants. It's actually forced to bond at an angle much, much smaller than it really likes to have from quantum mechanics. We'll get into it why. But it can bond, but it's just not going to be as stable because there's a lot of internal stress and tension on these bonds. So in other words, I can break these bonds a little bit easier because they're basically not relaxed. It's like they can hold on, but they're under a lot of internal tension there because they're not to the normal angle that the carbon really wants to maintain. Now we can go down 1 more instead of cyclobutane here and actually go to cyclopropane, where we actually have 3 carbons. Let me make this one a little bit smaller. We can have 3 carbons here. And it forms this triangular shape, and this is an even smaller bond angle. This bond angle is very far from 109.5 degrees, so there's even more strain. So when you get into organic chemistry and you learn about these hydrocarbons, especially the ones that have rings involved in them, you learn that the more strain that there is on some of these rings, then the less stable the molecule is, and the less life it's going to, the less probability you're going to have of finding it in this orientation, just because it's just not as stable as a larger ring chain. So now we've gone through and talked about a lot of hydrocarbons in terms of the alkanes, where there's a single bonds. Keep in mind there can be double bonds and triple bonds, but they're another class of organic molecules that we talk about in the future. We're just talking about the single bonds here with the alkanes. Now that we've done that, let's go and look at some other variety just really quickly to get some motivation. This is a caffeine molecule. And this is what you drink in your coffee. So each of these dark gray circles are carbons, and the red ones are oxygens. And notice that the oxygens have 2 lines connecting to them instead of 1 line. That's called a double bond. We're going to get to that later, but basically it just means more electrons are involved in the bonding on the double bond as opposed to the single lines here. Notice we have other double bonds down here. So the red balls here are oxygens, and the blue balls here are nitrogens. The gray balls are the carbons, and the ones on the end here are the hydrogens, just like they were before. So caffeine consists of 2 rings. One has 1, 2, 3, 4, 5, 6 atoms in the ring. And then this one down here has 5 atoms in the ring, and some of them are nitrogens, and you have these oxygens hanging off, but again, double bonded, not single bonded. Let's look at one more. This is table sugar. This is called sucrose, and it is a molecule that has a lot of carbons in there. And of course, the red ones are oxygens, so we have a lot of oxygens in there as well. And then we have hydrogens also. So table sugar, stuff you eat every day, has lots of carbons, lots of hydrogens, and lots of oxygens in it. All right, so now that we've done an overview of the alkanes, the long chain single bond carbon molecules we call alkanes, from up above, let's go back to the board and learn a little bit more about how to draw these molecules. All right, I hope you've enjoyed the computer demo here. It's always good to visualize 3-dimensionally what we're doing. So now we come back to reality and we have to try to name these carbon chains. You need to know the prefixes: meth, eth, prop, but. Those are the ones that are new. Methyl, ethyl, propyl, butyl. 1, 2, 3, 4. And then after that, they have the same prefixes as we've used before: penta, hexa, hepta, octa, nona, deca. And the number indicates how many carbons. So methyl, ethyl, propyl, butyl, 1, 2, 3, 4. After that, 5, 6, 7, 8, 9, 10. And there are words beyond 10 that we use in organic chemistry as well. And the number of hydrogens listed in each of these molecules is just the number of hydrogens to make sure that every carbon has 4 bonds. So if you have 2 carbons, then each of those carbons on the ends, we're going to need 3 hydrogens each. Remember from the computer, so that's going to be a total of 6 hydrogens in the 2 carbons. So these are the molecular formulas for each of these hydrocarbon compounds. All right, now what I think I want to do now, before we actually do our problems, is I want to build a couple of molecules with these models here. We've already done the computer, but I think there's something to be gained from actually holding something in our hand too. And so I think I'm going to do that. How do I want to do this? Let me push this back in place. And let's just talk for just a minute. So this is methane. We just saw that on the computer. We have a single central carbon. We have the 4 hydrogens, so it's CH4, right? That's what methane is. And the bonds here in between, the angles between the hydrogens along the carbon bonds wants to be 109.5 degrees. We learn why that is the case when we study bonding, okay? For now, just know that that's the maximum angle in 3-dimensional space that 4 things can reach whenever they all spread out from each other. So here is methane. Now, what I want to do next is show a model of ethane. All right, so this is ethane, C2H6. So there's 2 carbons, right, in the center there, and each of the carbon has to be connected to 3 hydrogens for a total of 4 bonds on each of the carbons. But notice that the angles here between the central angle bond between the 2 carbons and the hydrogen, and then this one and the 2 hydrogens on the end is the same angle as in the methane molecule, 109.5 degrees. So everything is trying to spread out and have the same angle as before. So this is a very simple molecule to understand. So it's a straight, there's no bending between the carbons because there's only 2 of them there. Now, one thing I do want to point out to you is that notice that these bonds since they're single bonds, they can rotate in 3-dimensional space. So you could have a situation where everything's lined up, the hydrogens are lined up. Notice all of these hydrogens are lined up. Or you could have a situation where, if you look at it end on like this, they're basically a staggered configuration where this hydrogen kind of fits between these, and this one fits between these, and so on like this. Now, of the 2 configurations, either you're looking at it like this, where everything is staggered, or you're looking at it like this, where everything is lined up. Which do you think is going to be the more likely configuration? Well, the molecules floating around, bumping into everything, can twist and turn, the bonds can move. It's going to be more likely to be found in the staggered configuration. Because around these hydrogens, we're going to learn later all about electron clouds, but basically the electrons are being shared between these guys, but they also exist all around these atoms here. And basically what's going on is there's an electron cloud here and an electron cloud here, and those electron clouds are trying to repel each other because like charges repel, right? So if you're in a situation where they're like this, they're closer together, they're going to try to repel each other until they reach a maximum distance apart, which is in the staggered configuration, okay? Like this. This is called eclipsing configuration. This is called the staggered configuration. And in general, this is going to be what we call the lower energy state of ethane. It's going to want to be staggered like this because of the repulsion happening among the hydrogen molecules. And this single bond here between the carbons can rotate. Of course, these can rotate too, but it doesn't do anything. I mean, it's a symmetrical thing. But when you rotate this, there's different forces acting, and so it's going to end up being more like this. So if we take this ethane and we remove one of these hydrogens, and then we add to it another carbon atom like this, which is what I'm going to do right here, and then I take one of these other hydrogens, if I can just hold this guy, it's going to be difficult for me to do this without dropping everything, but I'll try. All right, then we arrive at methyl ethyl propyl. Remember, let's go back to our list here. Methane, ethane, propane, that's 3 carbons. All right, so this is the carbon chain that has 3 carbons. And again, things are going to twist and turn because now you have 2 things that can move. You could have this that can move, you have this that can move, and things are going to arrange themselves in such a way to put the least amount of strain possible among the forces that are inside of this thing. I'm not going to go through them all because really that's stuff you learn in organic chemistry class. But basically just know this molecule is alive and it can twist and turn and so on, and it's going to arrange itself like that. So there's a 3-molecule chain. A 3-carbon chain, I should say. 3 hydrogens on each end, and then you have the 2 on the interior here. Now what's going to happen if I remove, if I can do it without breaking it, I remove this hydrogen right here, and I will add a carbon right here. And let me take this stick off and put that hydrogen back on that I just took off. All right. So here we are here's methane, ethane, propane, butane. So here is C4H10. Notice why you have 10 hydrogens, because you have 3 here, then 4, 5, then 6, 7, and then 8, 9, 10. You need that many to give every carbon 4 bonds. You can see that in this configuration, all of these hydrogens over here are going to be repelling each other. So they're more likely going to be that this molecule is going to generally want to flip around and look something closer to this. Now, how exactly? Maybe more like this. I mean, I can't tell you exactly by just looking at it. You have to really look at the details of it. But it could be like this, but then the repulsion between those the electrons around the hydrogens are probably going to force it to be more like this. So 4 carbons. So that's butyl, and then you have enough hydrogens to fit on there. Now you can connect, if you really work hard, you could take some of these hydrogens off and you could connect this into a ring. But notice how much strain there would be, right? Because the angles that these carbons like to bond at, quantum mechanically, what they like to bond at, everything likes to be spread out. So if I force it together, I could make it happen, but it would be a lot of internal stresses on what's going on. So what I'm going to do instead of trying to force this thing and break my model, is I'm going to take this off. I'm going to take the methane that I have over here, and I'm going to try to do this without breaking it, and see if I can connect this methane over here. There we go. All right, so how many carbons do we have here? We have 1, 2, 3, 4, 5, so that's pentane, right? Now, of course, it's not going to want to hang out like this because there's so much repulsion going on between the electrons surrounding the hydrogen atoms. It's much more likely to look something like this, right? And in fact, it's probably more likely to look something like that because everything can spread out. Of course, it could flip around like this, but it's probably going to have some repulsion coming into play. So it's probably going to look like something like this. This is a straight molecule of pentane, 5 carbons. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and you can see the 12 hydrogens there. Now this chain is long enough where if I do try to connect it into a ring, there's not going to be that much tension there. So I'm going to try to do that without destroying what I've done here. And probably I'm not going to be able to do a great job. But what I'll do is I'll just remove this one hydrogen. I'll grab another bond. I'll stick it into place over here. I will remove this other hydrogen from the other carbon on the other side, and I'm going to wait to connect it while we're all looking at it together. So all I did is remove the hydrogen from here and remove the hydrogen from here, and now what I'm going to do is connect them together. And you can see I can do it without too much tension there. There's a little bit, I had to push a little bit, but there's not too much tension. The larger the ring, the less tension there, because each carbon wants 109.5 degrees, right? That everything wants to spread out. So if you only have a 3 carbon or 4 carbon chain, it's actually a lot of tension and it's unstable molecule. This is a much more stable molecule like this. But notice that it's not exactly in the same plane. If you really look at it, it's not exactly where all of these are lined up. It's going to be kinked one way or another to try to give it more breathing room and have everything spread out. All right, so I just wanted to build a couple of models, mostly because they're fun, but the real reason that I want to build a couple of models is because it really helps us visualize what's going on. If you just draw these things, if you just draw all of the molecular formulas, then you completely miss the point, because organic chemistry is a 3-dimensional game. Right? Yes, I can tell you how many carbons and hydrogens, but there's different way to connect them. You see, with the pentane, I could connect them in a straight chain. I can also connect them in a ring. And then later, when you take organic chemistry, you'll learn that you can actually remove some of the hydrogens from the chain, and you can put other things, like maybe a chlorine in there, or maybe some other group of atoms that can fit on there, which we're going to talk about in just a minute. All right, so now what we want to do, now I think that we know a little bit about what we're talking about, is I want to compare a few different things. So let's talk about methane. Whoops. I want to talk about methane, right? And I'm going to write down the molecular formula, right? And then we're going to talk about something called the structural formula. Right? And then we're going to talk about something called the condensed structural formula. Right? So here we go. let's just talk about this. We're not going to write down too many of these. We're just going to do a few of them, but it's going to be very, very helpful. So let's talk about methane. The molecular formula of methane is CH4. It's the simplest one, right? So what would the structural formula be? The structural formula is an attempt to draw on paper something that kind of resembles the structure. Now, you know from looking at these that the structure is three-dimensional. So you can't represent the structure exactly on paper, right? In fact, there's a lot of different ways to draw organic chemistry molecules. We're not going to go into all the different ways. We're just going to write the basic structural formula down. And that is that carbon is in the center and it's connected to these 4 hydrogens. So there's a hydrogen there, there, and there. But this is not a great representation of methane, right? Because we saw that carbon's really in the center and in 3-dimensional it's like a tripod on the bottom with one sticking up. This does not represent or look like a tripod, but it still tells you that carbon's at the center connected to the hydrogens on the periphery. So it has some value, but it's not really totally accurate, but it's getting closer to what the thing looks like. All right. Now, if you don't want to write this all the time, you can write something down called the structural formula, which in this case, the condensed structural formula is exactly the same thing, CH4, as the molecular formula. So let's just leave it like that. When we get to ethane, you'll see what the difference really is. So next, let's go to ethane. Right. What is the molecular formula of ethane? Well, if you forget, all you can do is you can say, well, I know that ethane has 2 carbons bonded together and there's a single bond there. And I know that every carbon has to be connected to 1 hydrogen. So I know that it has to look something like this. And all of these are going to be hydrogens surrounding in the periphery like this. And this is ethane, all right? So we now know that we have C2, H, 1, 2, 3, 4, 5, 6, H, 6, which matches what we wrote down over here. The reason it has to be 6 hydrogens is because every carbon has to be bonded to 4 things, and since you have one here, you just count them up and that's what it is. All right? Now the condensed structural formula is a way of trying to write this in a way that gives some of the information about the structure, but not all the lines everywhere. So the way you would write it is you would write it CH3, CH3. Now compare these two things together. This one tells you how many atoms of each you have, but this one tells you sort of how they're connected. You have a CH3, which is a carbon and 3 hydrogens connect as a group, and they're connected to another CH3. So it's like CH3 connected to CH3. This is what it's trying to tell you. And you don't have to draw all the lines there. You can, in your mind, once you do this enough, visualize, okay, C connected to 3 hydrogens, C connected to 3 hydrogens, those are connected together. That's what this is intended to show you. It gives you an idea of the structure without drawing all of the details, but of course it's not as clear as drawing all the details. All right, so let's move on from ethane. We're going to do 2 more, and then we're going to be done with this. We're going to look at propane. Right? Now, if you're not sure of the molecular formula for propane, that's okay. If you remember methyl, ethyl, propyl, it must have 3 carbons, and we know they're all single bonds in an alkane. All of the single bond alkanes end in ane, right? If there is a double bond involved in the carbons, it's called an alkene. And everything ends in ene. If there's a triple bond involved between the carbons, it's an alkyne. You know, methine, ethyne, things like that, which would have a triple bond somewhere. Okay. So they would have an I and E, a Y and E there. But for anything that ends in A and E, you know because of the ending that there are single bonds for all the carbons, in between all the carbons. So if this is propane, where are the hydrogens going to go? Well, that one needs 3, this one only needs 2, and this one needs 3, and everything is just an H. You just put the H's here. Now this is great for visualizing, especially in the beginning, but you can see it's a pain to draw all these hydrogens because hydrocarbons always have enough hydrogens to make every carbon have 4 different bonds there. So we can write something called the condensed structural formula down. Now over here you can see there's a carbon and 3 hydrogens, so we write it as CH3, but this carbon only has 2 hydrogens, so we write it as CH2, and then this one again has 3 hydrogens, so we write it again as CH3, and this one is like a condensed way of writing this down where you can kind of see the structure once you know how these things are laid out without drawing all the lines. Now we could probably stop there because I think the point has been made, but let's just do one more. We're going to go to butane. Again, because there's an A and E, we know there's only single bonds between the carbons. And I forgot to mention the molecular formula here would be C3, and then we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. so C3H8. Now for butane, if you forget what the formula is, you've got to have 4 carbons. And then each carbon has to be connected to 4 things all together. So this is what it looks like, right? And these are all hydrogens, these for a hydrocarbon anyway. Now we're going to learn in just a minute that we can replace some of these hydrogens with other things and make a very, very, a rich array of things. All right, so what is the molecular formula here? 1, 2, 3, 4 carbons. And then we have 8 hydrogens, 9, 10. 10 hydrogens, like this. All right, what would be the condensed formula? Well, there's a CH3 group right here, CH3. But then this carbon only has 2 hydrogens. And then this carbon only has 2 hydrogens. But then this one has 3. So we're at CH3 for this one. So this would be the condensed structural formula. So you got to remember, this is just an introductory lesson to an to an entire class that you take in this stuff. And naming these organic compounds is a big task in and of itself once you get past these very simple molecules that we're talking about here. Because even just take the idea of butane. We just saw a picture that we could connect this thing into a ring. So the structural formula could form into a ring. And then from that ring, you could, instead of a hydrogen connected, you could connect something else to it, and it's a totally different molecule, right? In fact, that's what we're going to do in a second. So we're going to talk about, just briefly, how can you change one of these alkanes into something different? So that's called being a derivative of an alkane. Alkane is a carbon molecule chain, hydrocarbon chain with only single bonds. Alkane, single bonds. Alkenes is double bonds. Alkynes is triple bonds. We're not talking about any of the double or triple bonds in this lesson, all right? So what kinds of things can we substitute in? We have all these hydrogens here. What things could we do? Well, basically, we want to put things here that are going to want to share at least 1 electron. The reason hydrogen cozies up to the carbon is because each carbon wants to make 4 bonds, so every kind of side of the carbon wants to have an extra electron, and hydrogen also wants an extra electron, so they both come together. Since they each want an extra electron on each of the bonds here, then they partner up, and so they can each feel like they have 2 electrons here. Each of these lines kind of, to the elements, feel like 2 electrons, because 1 electron is coming from the carbon and the other electron's coming from the hydrogen. So each little dashed line that we call a bond, it's like 2 electrons being shared there. So what kinds of things could you connect? Instead of hydrogen, which wants 1 electron, you could put fluorine in place. Fluorine wants 1 more electron. Chlorine, bromine, iodine, they all want 1 more electron. But there's actually, above and beyond just substituting elements, there is an entire category of things called functional groups that can be substituted for the hydrogen. Now, this is not an organic chemistry class. We're not going into detail, but just know that when you take that class, there's an entire many chapters dedicated to the types of things and the functional groups that can connect to a carbon chain somehow, basically take the place of a hydrogen. And the most famous one is what we can use to form an alcohol, right? Now, there's lots of others, but we'll talk a little bit, just a brief minute about alcohol. Now, a functional group is what we can substitute here that changes the character of the original compound. If you just substitute something there, but it doesn't affect how the molecule behaves, it's really not called a functional group. It's a functional group if once you it's a group of atoms that when you substitute them onto the carbon chain in place of a hydrogen, it kind of changes the reactivity and changes the characteristics of the chain that you started with. So, for instance, there is a group, a functional group called the OH group, and this makes alcohols, right? And I know that's kind of a little weird. You're like, well, OH, why is that an alcohol? Well, what you in your mind know as an alcohol gets its character because of the substitution of one of these hydrogens with an OH group. And again, when you take organic chemistry, you learn about tons of different groups, functional groups that can be substituted onto chains and totally change how they behave. And that was part of the reason it gives rise to the richness of organic chemistry. So, for instance, methane, remember, is a single carbon, right, connected to 4 hydrogens, right? So there's a hydrogen here, and a hydrogen here, and a hydrogen here. But actually, if I put the hydrogen here, it's just called methane. But instead of putting a hydrogen here, I connect this functional group called the OH group right there, then this becomes an alcohol now. It's no longer methane anymore, but I guess I'll go underneath it. We call it meth. We still use meth because methane, it means it's connected to 4 things, but we call it methanol. And the OL at the end signifies that it's now an alcohol. So when you see methanol, you know that it's a carbon that was connected to 4 things, because methyl means methyl group, methane, but where one of the hydrogens now contains the functional group for alcohol, OH. And so it's substituted like this. This is called methanol. Now, when you originally started with methane, which was this thing, this is a colorless gas that is flammable, right? And when you replace just one of these things with the alcohol group, the OH group, it is no longer a gas anymore. It is a liquid, right? A liquid there. So it changes the character of what it is completely. Right, let's take a look at another one. Now, ethane. Ethane was, remember, we connect hydrogens to all of these guys. So we get hydrogen here, and here, and here, and here, and here. So if we connect the hydrogen right here, it's called ethane. But instead of connecting a hydrogen there, if we connect an OH group to it, it changes. It's no longer ethane anymore. We call it ethanol. And again, the OL tells you that it's an alcohol. And it's an alcohol connected to what was the shape called ethane. Remember, ethane was here, C2H6, and all we did is we replaced one of these guys with OH. Now notice that if we, instead of replacing this one, we replace this one with OH, then the molecule is the same. If you flip it around, it would be exactly the same. If you replace this with OH, it is slightly different, but will have the same character because it's still connected to the same carbon. So this is called ethanol. So that's where you start to see the richness of the naming come into place. Now this next one's very important, so I don't want you to fall asleep. I want you to pay attention. Let's talk about propane. So we have carbon, carbon, carbon. Remember, the sequence is methyl, ethyl, propyl. Propane, 3 carbons, and then all connected to enough hydrogens. Turns out to be 8 of them needed to round out the structure. So to make propane, we connect this all to hydrogens. What do you think we're going to do? We're going to connect it to an alcohol group and see what happens. So here we have an H, we have an H, 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 H. All right, now, instead of connecting this to a hydrogen, which would make it propane, a gas that's flammable and so on, we connect it to an OH group. And now it's an alcohol. What is it called? It's called propanol, right? Propanol. But you see, now we have an interesting situation, because if I connect it here, then of course it's connected to one of the carbons on the end of the chain. Instead of connected it here, if I connect it here, it's still the same molecule, because I could flip the whole thing around and it's still connected to a carbon again on the end of the chain. So if I connect it here or here, it's basically the same thing. But if I connect it here, it's actually functionally a little bit different. So to show the difference here, we actually call this 1-propanol. The 1 means that the OH group for the alcohol is connected to the first carbon, which just means one of the ends. It doesn't matter which end, because no matter which one you connect it to, you can flip it around, it's still the same thing. So 1-propanol means alcohol group connected to one of the end carbons. All right? So let's draw the other one here. So carbon, 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 everything needs 4 bonds, everything needs 4 bonds, like this. So hydrogen, 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 and hydrogen. Now, instead of being connected to the end point, we connect it, let's say, here, where the oxygen's bonded here and there's a hydrogen bonded there. So it's an OH group bonded like this. So it's in a different location, but it's still propanol. It's still a 3-carbon chain with an alcohol attached. So we can still call it propanol, right? However, instead of a number 1, we put it as a number 2. We call it 2-propanol. And that means, and it tells us that it's still propanol, but the alcohol group is connected to the center carbon, which is the number 2 in the chain. So you number the carbons in the chain, this would be the number 2. Now, I'm not going to go beyond this because this is just an introductory lesson to this whole thing. But when you have much longer chains, like let's say you had octane, that's 8 carbons, and you hung an alcohol on like the 4th one, then it's not going to be 1 or 2, it's going to be number 4 named appropriately. I'm not going to get into the naming structure because there's a whole lot of exceptions. Like what if it's done this way? What if there's a branch? What if one of the carbons branches off? Like how do you name the chain? Because right now I'm drawing all these as a straight carbon chain, but I think because these behave like Tinker Toys, I could have a long branch of carbon and then another branch of carbon coming off the top. And then I could have the OH group hanging up off the top part instead of on the bottom part. So I have to have a concrete way of naming these things. So when you get into organic chemistry, there's a whole chapter on how do you name these things. The first thing you have to do is identify the longest chain that's in your structure, and then everything is numbered on that chain, and then you put it all together, okay? So there's a process to it. So I'm not gonna go any farther than this. But these things here, when you have, notice there's 3 carbons, and then the same number of hydrogens, and then we have an OH group. Same number of carbons, same number of hydrogens, and then we have an OH group. So we have the same number of atoms, the same molecular formula. However, the structure of it is different because this is bonded in a different place. This concept is called isomer. They're isomers. Isomers are basically 2 different molecules that have the same atoms, the same number and type of atoms. So if I just wrote down the formula for it, then it would appear to be the same, but the structure is different, and that's called an isomer. Now that's extremely important in organic chemistry because the isomer, the shape of the molecule, a lot of times dictates how it reacts. You may have the same atoms and the same, the same molecular formula, but the shape of it in three-dimensional shapes, in three-dimensional space, will dictate how it reacts and what it does. So most of organic chemistry isn't just, that's why we don't write the things like this a lot of times. We write it using a structure, a way of drawing these molecules. We call them line drawings, but I haven't even shown you that. There's a shorthand way of writing all these chains that you learn in organic chemistry, and we do that because the structure of the thing, if it's different, will make it behave differently in most cases. All right? Now that we've done all this, which is kind of a long introduction, I do want to solve a couple of quick problems, which I think will be very easy for us to conquer together. All right, we want to determine if each of these molecules are organic or inorganic. Inorganic or organic, if you could say that a lot, 5 times fast. So here we have calcium, and then we have CO3, all right? So the question you need to ask yourself, if something is organic or not, is does it contain carbon? Does it contain hydrogen, okay? And in general, that's going to be enough to tell you. I will tell you that in most organic molecules, you're not going to find metals. You're generally not going to find metals. You're going to find carbons, you're going to find hydrogens, and you're going to find things that can be substituted on for the hydrogens, like I told you, iodine, fluorine, those elements that want to gain 1 electron just like hydrogen, and then certain functional groups that also like to attach. Things like calcium, they're not going to attach to a hydrocarbon chain like that because calcium wants to lose an electron, doesn't want to gain an electron. So right away, you see there's a metal in here, and there's also no hydrogens in here at all, so this thing is inorganic, even though it contains carbon. Inorganic. Needs to have, it needs to have carbon and hydrogen. All right, next problem. Let's take a look at C4H8. Is this organic or inorganic? Okay, it's got carbon, it's got hydrogen, nothing else, so this thing is organic. Whatever it is, it's organic. Next, C3H6O6. Organic or not? Well, it's got carbon, it's got hydrogen, so that part's good. It also has oxygen. It's perfectly fine to have oxygens in organic molecules. We saw it in some of the molecules on the computer screen there. So you can have oxygen in your molecules, but you must have carbon and you must have hydrogen. And so that's what we have, so this is organic. Okay? And then our last one, which is D actually, is LiF. So this is lithium and fluorine. There's no carbon, there's no hydrogen, and obviously this is not organic because it has a metal and a non-metal. So this thing is inorganic. All right, easy enough. All right, next, our last problem for this lesson. Draw a structural formula for pentane which is an alkane with a 5-carbon chain. We talked about that. What are pentane's empirical formula and molecular formula? What is the definition of a hydrocarbon? Some of this is a rehash of what I just told you, just to try to make sure we all understand. First of all, what is pentane? Pentane is a 5-carbon chain, right? So the way we do this is we connect 5 carbons, 2, 3, 4, 5. And we know that each of these carbons has to have 4 bonds. So we just draw all the bonds, and we know that the interiors have 2 and the exteriors have 3. And then everything has to be connected to a hydrogen if it's just a pure pentane molecule with no functional groups or anything substituted on it. So here we go. A lot of drawing of H's, right? So this would be the structural formula for pentane. Right, that's it. What would be the molecular formula? Molecular formula. Well, it's C, 1, 2, 3, 4, 5. H, here we have 10, and then 11, 12. H12. All right, now we ask ourselves next, what's the empirical formula? Empirical formula. Empirical is when we take the molecular formula and we try to reduce it down to some smaller ratio. But in this case, we have a 5 and a 12, so there's really no way to divide both of these numbers by anything smaller. So the empirical formula in this case is actually the same as the molecular formula, right? Because we can't simplify it anymore. If instead we had like C6, H14, then we would have even numbers, and we could then divide those numbers by 2, for instance, or some other number to make it smaller, and we could get the smallest ratio between the elements. But in this case, there's nothing, we can't do that because they're already reduced. And the last part is, what is a hydrocarbon? It is a carbon molecule where we only have carbons and hydrogens. That's it, nothing else. And the carbons are always going to have 4 bonds. So we're going to have enough hydrogens to saturate that carbon chain so that every carbon has 4 bonds. So often what happens, or all the time what happens, is the carbons on the end get the 3 hydrogens, and the carbons in the middle end up getting 2 each, and that's why the formulas look the way they do. So we have done a tremendous amount in this lesson. I could have cut it short. I didn't really have to do the computer stuff. You know, I could have just said, here's a hydrocarbon. But I really want to also motivate you. I want you to look at it and say, wow, that's neat. Right? And understand that it's understandable, right? If I just throw it at you, methyl, ethyl, propyl, butyl, and penta, and all this, and say, blah, 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 it just doesn't seem very exciting. But I think that when we look at the 3-dimensional structure, when we hold a molecule in our hand and we see how it fits, and we twist it and turn it and see how the hydrogens might line up or how they might not line up, it comes a little more alive to me. And then when you get into organic chemistry later, you realize that the reactivity of this thing is going to be different, not only based on what's in the thing, but how it's oriented in 3-dimensional space is also going to dictate how it reacts. And that's why organic chemistry is such a broad and varied subject with lots of different topics, because there's just a lot of different ways in which things can happen depending on how they're oriented in 3D space. So I'd like you to watch this a couple times. I did spend quite a bit of time on the computer stuff and the models. I think all of it's important and relevant. And then follow me on to the next lesson. We'll wrap up the concept of simple organic compounds.